Life is not a game, but preparing for harder times can still be like one. Develop the skills to thrive in a tougher world, while it can still be fun to acquire them. What I'm trying to say is that we have probably all noticed that the near future doesn't look so bright. Many of us are already struggling with increasing inflation, and it becomes more and more apparent that we will keep seeing shortages in goods of daily use as well as in some forms of energy. More and more people are also raising the question if the system of international trade and global shipping can exist forever in the way we've seen over the past years. A transition to another system of more local production and distribution of goods is absolutely called for. But such a transition to that system will most likely not happen without even more disruptions. In that sense, much of the work that I show here would not seem economical or even reasonable under the conditions many have come to know as normal. But if that paradigm were to shift, many would find themselves in a miserable situation, and learning how to reclaim things and build things for yourself would be a game no longer. In that sense, let's visit some scrapyards and see what we can find there today. Looks like someone also built a bicycle trailer here, or rather someone slapped a lot of additional material on an existing trailer, but I think I already have one. An old Jerrycan. Might seem insignificant, but this is actually an interesting find. What do we have here? A neon sign transformer, and we'll take that home. And over here a pretty awesome steel cabinet, another keeper. Other items that I found earlier that we will need today as well is this ammunition box of the German army, this steel enclosure, and this uninterruptible power supply that we will use to build another island-type photovoltaic system in this episode. So let's get back to the workshop then. Let us start with something simple then. The old Jerrycan. And I guess there are a number of explanations needed here for various groups of people. Now, first of all, what are these cans actually called and what is significant about them? The reason they are often referred to as Jerrycans in English is that they were invented in Germany, with Jerry being one of many nicknames for the German people at that time. And that time were the pre-war 1930s. Since the German armed forces were officially renamed Wehrmacht in 1935, these canisters were coined Wehrmacht Einheitskanister, which simply means as much as unified or standardized canister of the German forces. Today, a similar design is still in use and is often called NATO canister or something similar. The interesting thing is that even though an often overlooked item of daily use, it is actually surprisingly sophisticated in its design and was actually a matter of espionage and national security in World War II. The main reason being that many pre-war gas canisters in both Germany and many of the Allied countries were poorly designed and had even nicknames that reflected that, like the British flimsy. To name some of the features, the triple handles allow one person to carry either 2 full canisters using the handle in the middle, or 4 empty canisters gripping 2 of the outer handles with each hand. The 2 outer handles also make it easier for 2 people to carry one can together. The flip-top closure doesn't require tools to open and close, an innovation at the time. The gas cap also can't get lost. It has more pretty brilliant design features and was copied rather quickly by various countries in World War II, even though many of the copies were of lower quality. If you want to know more about that, I have put some links in the video description. In terms of repairs, there wasn't much to do here, so let's get on to the next item then. This cabinet with its square handles must be pretty old. It is also super heavy and I had a hard time getting it home. I think that it probably used to be a filing cabinet, but it should be rugged enough to store tools as well. The old paint was removed by wire wheeling, but on second thought I should have used paint stripper instead, because of the mess we needed to create to get all the old paint off. Wire wheeling usually works very well, but it has the problem that it spreads so much dust and chipped off paint around, which will eventually find its way into the environment, so sometimes it's better to use paint stripper, even though that's nasty as well, but at least you can collect it much easier. A new paint job was applied then, and now I can finally start my own X-Files collection. Projects like these are nice scores for me, but they don't necessarily make for the most endearing projects. So let's have a look at something way more challenging then. Let's have a look at this UPS or uninterruptible power supply then. From the outside, it's really just a black box with a battery connector that happens to stick out in the front. After removing the screws though, the enclosure can simply be slit open, allowing us to have a look inside. The empty space is where you would normally find a set of lead-acid batteries. Since this is a 24-volt system, and considering the form factor, I suspect that it would have had 4 6-volt batteries connected in series. We also find a big PCB, which, among other things, contains a sine inverter circuit and some form of charger to charge the lead-acid batteries from the mains electricity. The flat magnetic component with the yellow insulation is an autotransformer, used to correct a possible undervoltage condition in the power grid. Now, what are my plans with this UPS? Well, some weeks ago in episode 29 of this series, I already worked on another uninterruptible power supply, as some of you might remember. Similar to what I did with that other unit, I want to try to build an island photovoltaic system around this UPS. But this time a few things will be different. First of all, it will be a 24-volt system instead of a 48-volt system. And the next big difference is that this topology of sine inverter works without a chunky mains transformer. This unit is also only rated for a maximum apparent power rating of 600 VA. It will therefore not be suited for heavy machines and power tools, but I was thinking that it could be possible to power the lights of my workshop from this inverter. In order to improve its long-term performance and to make it easier to service and test, I will change a few things here though. An autotransformer, in German Spartransformator, is different from ordinary mains transformers in that it only has one winding, which also means that it doesn't offer electric isolation. Its advantage though is that you can build a transformer of the same power rating in a smaller form factor, and thus also with less material needed and for lower cost. In some uninterruptible power supplies, a mains transformer is part of the output stage of the inverter, but then the output winding is also tapped to act as a step-up transformer when the mains voltage is too low, like in a brownout scenario. In this case, however, the transformerless inverter and the auto transformer act completely independently, and we can hence just remove it. We can also remove the other external boards that connect to the main board. And just in order to show you that this works in principle, I have now connected two 12-volt batteries and a power drill to this board. The UPS board will be part of an experiment in which we will have to determine if this device, which was made for short-term service in emergency situations, can act as an inverter in a setup where it is expected to run for much longer hours. Hence, in order to allow for better cooling and accessibility, I will now transplant that PCB into this bigger and more rugged enclosure from the scrap. Since it still has some markings on it, I use some acetone and then some degreaser to clean the outside. In the next step, an angle grinder is used to cut out the piece of sheet metal to which the board was fastened before. It's handy to reuse it, and you'll see why in just a minute. See, it is riveted to this steel plate that goes into the new enclosure. And the cool thing about the old piece of sheet metal is that it already has all the threads needed, and it also came with this white piece of insulation that fits right between board and enclosure. It's just the right size too. In the next step, a plastic part was designed with Fusion 360 and is now being printed on the 3D printer that I borrowed from my friend. It's really about time I get my own. This plastic part will not only close the enclosure, but will also house a bigger fan than the tiny one that came with the UPS. A dust filter is installed as well, in order to prevent dust from clogging up the heat sinks and electronic components. When connecting fans to sockets or connectors of fans from other manufacturers, it's often necessary to look up the pinouts and color codes. They can be rather different, as you see here. I also integrated some battery terminals into this plastic part, even though, seeing it now, it would be safer to place them wider apart and also use bolts from materials with better conductive properties than galvanized steel, but I simply didn't have anything better at hand. The conductive cross-section area of these wires is also on the lower end of what you should use, and with 20 or more amps flowing, they will get rather hot. I'm aware of that, but these videos take an eternity as it is, and I can't always wait until all the perfect components are available. Just be aware that you should use thicker wires here. Under the PCB, I also install this rail so that I can fasten some proper clamps here for the output side of the inverter. Protective earth wires are also connected to various parts of the enclosure, and the inverter will also have to be earthed when it's installed. I then decided to also install an air vent on the bottom side of the box so that the air can flow right through the enclosure. There also is a second fan down there, but I'm actually not planning to use it. The heat sinks of the inverter are simple square blocks of aluminium. Normally, heat sinks are extrusions with cooling fins, maximizing the surface area of the heat sinks. In this case, we have a lot of mass, but not a lot of area. They tried to fit the heat sinks into a very low profile enclosure, and I also believe that they designed the UPS in this way because it is normally built to run for only a short amount of time. The maximum duration would be determined by the rated maximum apparent output power of the inverter and the limited capacity of the batteries. Once they are drained, the inverter stops working and it only has to work up to that point in time, which was probably just a few minutes under full load. So in order to improve the performance of these heat sinks, I have now first drilled a few holes and tapped them. And now I'm cutting these salvaged heat sinks so that they will fit on the already existing ones. Then a layer of thermal compound is applied and the heatsink extensions are bolted in place. So after making all these changes, the next question that came to mind is where we could test our solar setup then. This freestanding wall marks the boundary between this and the neighboring property. It once belonged to a building that no longer stands, and all that is left is this massive brick wall. As you can see, I have installed this steel shelf here and it's fairly empty at the moment. If I were to install some solar panels on my roof, this would be a place where an inverter and batteries would be protected from rain and direct sunlight, while also being in a spot where there is not much that could catch fire in case the inverter, the batteries, or any other part of this experiment would overheat. So I drilled some holes into the bricks, and now the gray enclosure could be placed on the wall inside the shelves. I'm also already working on some metal doors to actually completely close off the shelf here, like a cabinet. The next step was to add some batteries. I wanted to find an enclosure for those as well. It should protect them from the outside world, but also be easy to move around. And I decided to use this ammunition box. The box is super rugged, but I also need something that acts as an insulator while holding the batteries down so that there could be no accidental short circuits, even if the battery enclosure was somehow mishandled. So I remembered the design for some plastic battery compartments that I had recently come up with for my solar e-bike trailer. I ordered 4 more of the same type of AGM battery and printed out 4 more identical compartments. I bolted the 3D printed compartments onto the bottom of the ammunition box. In the next step, I also added a vent hole to the front and also some holes for the battery connections. Since we're dealing with a 24-volt inverter, I used two parallel strings of two 12-volt batteries in series. I tried to use the exact same length of wire for all batteries so that the wire resistances would be close to identical. I wish I had some kind of very high current jacks or connectors that I could install to the walls of these boxes. Instead, I'm running the leads to the outside through these holes. And I added several layers of heat shrink here so that the wire insulation wouldn't be damaged by rubbing against the steel edges. Not too far from the shelves, I climbed up a ladder and on top of the flat roof of the workshop. As you can see, there is lots of space for solar panels here, but for this experiment, 2 will be enough. A little later, I also adjusted the orientation of these panels so that they faced south and placed them at a slight angle. Next, I needed a charger, and I decided to use this model here that I had also used for my bicycle trailer in my last video. But even though I'm using it here, I must say that I'm not a fan of these cheap Chinese solar chargers. At least this one seems to be an MPPT charger. It fails in other regards though. It is advertised as a 100 ampere charger, but in reality it can't handle nearly as much current. In fact, the clamps are so small that they cannot accommodate wires that I would call acceptable for a fraction of that rating. I would be particularly careful with the size of the load that you attach on the output on the right. This charger, for example, will start overheating at 15 to 20 amps and could literally go up in smoke. So if you have bigger loads in mind, attach them to the battery directly. In the future, I will only buy quality chargers or build them myself, period. For the time being, however, we'll use this one, and I want to protect it as well. And for that purpose, I'm removing the rail from this little protective enclosure, and I turn it by 90 degrees. This is not how it was originally intended, but you gotta admit that it fits pretty well. So I installed the little enclosure on that wall as well, and connected all the components with wires. Okay, so the solar panels are charging the battery pack, and the battery pack is powering the inverter. And as you can see, that little fan is running. It's running on solar power. So the whole thing works in principle, and I think it doesn't even look that bad. But I think we still need some kind of controllable or adjustable dummy load so that we can actually test what the inverter can and can't handle and how long it can handle it. So I guess we will have to build a dummy load then, and let's not waste any time. What does or doesn't constitute a dummy load is a matter of definition. In this case, it means that we want to burden a given electric source with an electric load of a known size in order to learn about the ability of that source to operate under that burden, while for the moment we don't really care what happens with the electric energy. It's just dumped. The very purpose of the dummy load is to just be a burden, and ideally one that we can adjust. In the past I have built different dummy loads of varying degrees of complexity. This one though will be really primitive. I bought 20 old-fashioned 75-watt incandescent light bulbs from a guy in East Germany for this experiment. For lighting my shop I only use LED lamps at this point, but for this purpose we want something that needs a lot of power and which acts as a resistive load. And here is what I did then. I also got myself 20 Edison-style sockets and took a piece of plywood from my pile of offcuts. Measurements were taken and a grid pattern was drawn. After reducing the size of the board with a jigsaw, 20 holes were drilled. The sockets were screwed to the board, and then 2 more offcuts were used as supports. If we just connected all these bulbs in parallel now, we'd have a 1500 watts dummy load, but it wouldn't be adjustable. So what I needed next were some switches. These are a bunch of new old stock switches that were manufactured for CRT TV sets. But then CRTs became obsolete and so did these switches. I bought them years ago for a few cents a piece. Their only downside is that they were always unpractical to install on panels. But the 3D printer has again opened up new possibilities here. 2-part adapters were printed and then the switches were glued to them. They could now simply be mounted to the plywood board. In the next step, the sockets and switches were connected to each other. Since I didn't want to waste 20 switches on this contraption, only 4 bulbs will be switched individually, while the other 16 will be connected in pairs of 4. This way we will still be able to select any number from 1 to 20 bulbs. The fact that the bulbs seem to change their brightness and light color here in this footage is just an illusion. This happens because of the automatic brightness adjustment of the camera. After having built this dummy load, I proceeded testing the inverter for many hours. I let it run with various loads and checked the heat sinks, chokes and other power components for overheating regularly. The 600 VA inverter can handle 600 watts for some time, but when you jump from 525 to 600 watts, it starts giving an overload warning. Until now, it looks like it can run for an extended amount of time in the 400 to 500 watt range. That is not tremendously much, of course, but it is more than double what you need for the lighting of the entire workshop. So now that we're done with that, we can still have a brief look at this neon sign transformer here. Since I don't have the equipment here to easily build a neon tube to test the transformer that way, we can just hook it up to the isolation transformer, slowly stepping up the supply voltage and see if we can create an arc. And I want to say in all clarity that this is not a particularly safe setup, and I absolutely do not recommend that you play around with these high voltage transformers yourself. However, I hope that you liked this episode. And if that is the case, and if you want to see more Repair-A-Thons in the future, please let me know by giving this video a like. And in case you want to support me more actively in this endeavor, please consider donating. A PayPal link is down in the video description, or become a supporter on Patreon under patreon.com/tpai. See you soon.